Yes, sir.
So we will start from the second assignment. So first question is actually there is a Fourier transformation. That is x of t is x of f. So suppose if some signal x of t has a Fourier transformation of small x of minus f, then we have to comment that xt, this one, can only be a real signal. So you have to comment whether it is true or false. Okay, so let's solve it. So it is the signal which has the Fourier transform x of f. And similarly, x of t, if that is the function, then it is given by x of minus f. Then we can say that this x of f, it is actually minus infinite to infinite x of t e to the power minus j 2 pi ft dt. Now, with the conditions that is given here, actually, it says that if I take the Fourier transformation of x of t, then it can become x of minus f. This is the condition. So following this, we can use the double Fourier transformation here, actually, like Fourier transformation of the Fourier transformation of x of t is equal to x of minus t. So if we take the Fourier transformation of x of t, it is actually x of minus f. So the statement that is asking that if xt only can be a real signal if the given property holds. However, there is a condition like this: x of t is equal to x of minus f. And this is a result of inherent properties of Fourier transforms. And it does not strictly equal xt to be real. Does not equal that xt should be real. Does not mean that. So it does not mean that every time it should be a real, only a real signal. It's no such boundary. It may be the real signal that holds, but it not can only be this part is false here. So it's actually false.
Sir, based on the duality principle, right? Of the
Yes,
Fourier
yes, yes.
transform.
Based on the duality principle. Because duality property also applies to both real and complex signals, right?
Yes. Yeah.
The second question here. Now you have to calculate what is the Fourier transformation of delta t. Okay. So it's pretty simple. So Fourier transformation of delta t, if you want to calculate it, it's actually from minus infinite to infinite tail of t e to the power minus j omega t dt. So for t equals to 0, this delta t is only 1. So this will have a value of to the power minus j omega to 0. Because only for t equal to 0, this will have a value 1. So this is equal to 1. So Fourier transformation of delta t equals to 1. So I'm going to the next question now.
Yes.
Yes. Oh. So the next question, if a signal is even function in time domain, then in frequency domain, what it would be? Like real imaginary, real or complex. Okay. Solve this. So it's even in the time domain means xt is equal to x of minus t. So if we look about the Fourier transformation x of a, that is actually integration from minus infinite to infinite x of t e to the power minus j 2 pi f t dt. So if xt is even, then it means that x of f is equal to, here it is equal to x of minus t. So it is actually x star f. How that comes? Because if we take it like this, minus infinite to infinite, it will become x of minus t and e to the power minus j by f t. Because if we take a conjugate term here, that is actually, it is even, so it does not change. Only this part, this negative part just comes like, or here I just wrote it more. So if we just substitute t is equal to minus t, we get this equation. And then if we just apply the conjugation here, again, it will become minus infinite to infinite x of minus t to the power minus j 2 pi ft. So that's why x of f becomes equal to x of minus f. As x of, so it I can again write it as minus infinite to infinite x of t e to the power minus j 2 pi ft. So so x of f becomes, here I take x transpose of f here. So x of f is equal to x transpose of f. And also x of f is equal to x of minus f. So the conclusion is, if a signal is even, in time, the Fourier transformation will be real. This is because x of f is equal to x star f. This is only possible when a function is real.
Real.
So you have to only derive what is whether x of f is equal to x star of f. So we started with x of f, then we substitute x of t is equal to x minus t property here. Then we calculated the conjugation property here. And then we just substituted x of t. This conjugation will come here also. So mode of those are same because the xt is also real. So then x of f is equal to x of x star of f, and then the function is real. So it should be real. Okay, so to the next question now. It's also from some duality property. So let a signal gt is defined by g of t sin t by t. Then find the Fourier transformation of a into g of minus t. So here first again there is the property like is gt is the event function. So g of t is equal to g of minus t. That type of thing we can write. So if a particular signal xt is there and this has a rect signal representation like this is the time period, then it has a Fourier transformation. You know that x of f is equal to at sec pi f t. So this is the if there is a signal in time domain like a rectangular shaped signal between of a time period t that is minus t by 2 to plus t by 2 here it is like this signal minus t by 2 to t by 2 a this sort of signal will have this sort of representation a seek representation in Fourier domain. So So from this property, we can write, and duality, using duality, we can write that Fourier transformation of x of t is equal to a by t using duality. We should write it. F by t. From the duality property, from this equation, we use the duality here. Now substitute t is equal to 1 by pi. And now, instead of xt, we just put here gt. Because gt is the sink here. You can see this is a sink function. This can be written as a by the rect signal, and it is f by t. So this is actually a, this is pi will come. From this is pi, then there is a rect signal, this is rect of f by t. This will be a square function because it's a sink function and its counterpart will be a rect. Now we just get another question. If we keep the same function here and we are just interested to find now I change the question, find the energy of a signal that is 2 of gt. What will be the answer? So remember, what is energy of a signal? That is actually this one. There will be, sorry, we just first we generalize and then I will do it. It is actually x square of t. And if you say the Parseval's relationship, that if you take the summation from minus infinite to infinite over x square t in this region, this the same energy will be conserved in the frequency domain too. So we calculate the energy in the time domain. Energy is not created or destroyed, so it also stays same in the frequency domain. So in the frequency domain, how do you take the amplitude? It is actually x of f square df. Now we know what is the x of f here. This is the x of f. So from here, we just can calculate the energy like this. So we have to calculate this value from Parseval's theorem. Mod of x of f square df minus infinite to infinite. And this is equal to this function. So just we can write from 1 by 2 pi to minus 1 by 2 pi, because the period is t is equal to 1 by pi. So t by 2 will be 1 by 2 pi. So we substitute from this is minus t by 2 and this is t by 2. And then we have to take the square of this because mod square. So it is actually a square pi square and rect function. The rect function is constant over this time. So that is 1 into t. Because if we take this function, it has a magnitude of a pi, and this rect function is what? It is rect function is 1 for this particular duration, and otherwise it is 0 behind this duration. So that's why this 1 comes in. So it is equal to a square pi square into minus half pi half minus half pi to half pi t. It comes a square pi. Now what is a? The value of a here? We just generalized a is equal to 2. So it is equal to
2, right?
2 square. So that is, yeah, 2 square pi. That is 4 pi. So this is how you have a particular, the connection is you have a GT, but it is sync. So if you directly go to calculate the energy in this domain, it will be a very complex function. Sin t by t square tt minus infinite to infinite. So it's very tough to calculate in this domain if I just directly ask you to calculate the energy. So what trick we take? We converted it, we just calculated what is the Fourier transformation. And we see that Fourier transformation is a rect function. That is very easy to calculate. Like its integration calculate the integration of this same thing is very easy. So the fundamental thing is here just is like this. Suppose you have a particular very complex signal. In time domain. Like here it was sync. So you have to calculate the infinite to infinite sync square dt. But rather, if sync is some sort of periodic in nature, right? Here you can see. It has a small
It's
period.
a power signal, right?
Yes.
So it's a power signal, right? It extends from minus infinity to infinity. So I think
It's not power signal because it's actually converging. If t tends to 0, so what is sync? Sync is equal to sin t by t. This type of format. So if t becomes infinite, this becomes 0, right? Because this, sorry. We can think like that it converges to 0, actually.
oh,
That type of thing happens here.
oh, like e raised to minus t, right? Mod e raised to minus t also. Ut.
Yes?
Like the function e raised to minus t ut you have discussed in the previous session, I think.
In the previous session, what I discussed, I am not understanding. Was it?
like in the previous session, you told that the function e raised to minus t ut is a, like it's a converging function, right? E raised to minus.
It's a converging function. You can
Oh, okay.
from the visualization you can see that
Yes.
because it's divided by a factor t.
Oh,
So that's why it's just if you calculate in the end, in the infinite, we can think that this function is converged.
that's
But if you want to calculate, you have to calculate a very big function like sine t by t. We have to
uh,
do the integration over this function, sine square t by t square.
oh,
So
complicated.
this is difficult. So rather, we see that it has some sort of periodicity. So the concept is we'll get a good frequency driven representation that is represent bounded by this particular square wave. So performing the integration over the small region is very easy compared to the sinc function that goes from minus infinite to infinite. So that's why just convert it to the particular rect function. If you know that this is a sinc function or some multiplication of some other sinc functions, and then just calculate the energy from the dispersible relationship. So basically, Percival relationship says that energy does not get changed if you calculate it within time domain or if you calculate in the frequency domain.
Sir, can you go to the next slide? Of the problem.
Here,
Yeah. Sir, you took here ET, right? Since we are calculating in frequency domain, it should
uh,
be F, right?
yeah, this
D.
is F.
Okay. Okay. Bottom
Sorry,
one.
this
Oh,
I wrote
uh,
as it should be F. Sorry.
oh, okay. Okay. The F is saying from minus 1 by 2 pi to 1 by 2 pi, right? In the bottom also.
Yes, F is from minus 1 by 2 pi to 2 pi because this
Oh,
is bounded by this rate signal.
right.
So even if you take anything beyond this point, that is 0. So that's why I took minus 1 by 2 pi to 1 by 2 pi.
Okay. The period is 1 by pi, right?
This is minus
That's
1 by 2 pi, this is 1 by 2 pi.
okay.
Beyond this signal is 0. So
Okay.
there is no point of taking other points. So basically, it's actually taking the area under this curve.
This, yes, sir.
Yeah. Now let us go to the sixth question. Suppose there is a signal yt. So yt is given by this equation. Yt equals to, it takes a value, two value it can take. It can take b or minus b. So it takes b if t less than equal to 0 and minus b if t greater than 0. So the question is, I am giving you four representation and you have to say which can be represented at which is a good representation. So So YT has which of them is the most accurate representation of YT? So there is three options. Which of them is the good representation of yt? Okay, so basically first we just try to draw the signal yt, then it will be clear. Yt is actually for t less than 0 and minus b for t greater than 0. Which is b for t less than equal to 0. So is this signal and this. So mark the signal, we just use the black. This is b, this is minus b. And suppose we want to just draw now, we just say that there is a signal like this. Now, if we just calculate it, we can see that this b, we can write it yt is equal to actually, in terms of if a unit step function, it is actually u of minus t, because this is the u of minus t part, this is u of minus t minus u of t, because this is the negative part. So this is bu minus t and this is bu t, and it is negative. So this negative is here. So we can rewrite it like this. And now if we calculate about limit a tends to 0 e to the power minus at, what it will be? If a tends to 0, all the values will be if nearly 1. It tends to 0 is 1. So according to this is actually, we can next slide. It's better to note. So limit a tends to 0 e to the power minus at is actually limit a tends to 0 e to the power at, and this is equal to 1, because a tends to 0, hence it 0 tends to 0, 1. So both of them have the same sort of value. So we can write it as, right now, this equation, because it is minus t, it is taking that value and ut is taking that value. we can directly write the fact that p of u of minus t minus u of t is equal to p of limit a tends to 0 e to the power at into u of minus t minus e to the power minus at u of t. So in this part, for t less than 0, this will be u of minus t. And for t greater than 0, this will be u of t. So this is the answer.
So it's the negative of the signum function, right? We have taken
What is this?
like a negative of the signum function multiplied by p. Yeah,
Yeah, signum function, if you are taking that, this is the negative of the signum
negative of
function.
signum function.
Yes, yes.
So, but in this case, sir, we are not taking zero, right? Since the zero, at zero it is not defined. Uh,
If you take t equals to 0, then both of them it is actually 0. So that there
oh,
is a discontinuity in the 0.
zero, yeah.
Okay. So the next question is actually you have to find the Fourier transformation of this particular function yt. Next question is find. So this is the right option. You just cannot add them up or just cannot take the half. So this was the right option. So what is the Fourier transformation of yt? That is the question. Okay. So already you have calculated what is the Fourier transformation, right? Here. Sorry, this representation. We have not calculated the Fourier transformation. We have got a representation of this order, right? So right now here, we just try to follow the linearity property of Fourier transforms. That is, suppose we have a signal A of xt plus b of x2t. If we then if xt has a Fourier transformation of x of f and x2t has a Fourier transformation of x2 of f, then we can write it as axf plus b x2 f. So here also these parts are like this. This is one part, this is another part. So first what we do here, actually we try to find out what is the Fourier transformation of this particular signal. That is actually so there is two parts. First part is e to the power minus at u of t, and another part is e to the power at u of minus t. So this has a Fourier transformation of 1 by a plus j omega, and this has a Fourier transformation of 1 by a minus j omega. These are very easy. So basically, how you do? You just calculate it over j omega t d omega, and then from minus infinity to infinity. So this this function just adds up minus 82 and j omega, and you get 1 by a plus j omega term. Similarly, here you will get a minus j omega term. So from here, you can just, so basically how we started it, if we take this function and this function, we know what are the Fourier transformation corresponding to these particular things. Then you just have to replace here according to the linearity equation of Fourier transformation. It is xt and xf, you have to just put it. So basically what we are trying to focus is this. So it actually becomes limit a tends to 0. And then what? Then first term is b e to the power at u minus t. So what was the Fourier transform of e to the power at u minus t? Is 1 by a minus j omega. So b, skip d outside. Alright. B is the outside because there is a b of term. And then I am just putting the Fourier transforms a minus j omega from here. And then e to the power minus at ut has a Fourier transform of a j omega. So just put a j omega. A j omega. So then it is a minus b and a plus b. So it becomes limit a tends to 0 b by 2 j omega by a square plus omega square. And there is a factor a also. Wait a minute, just let me check it. Sorry.
Sir, thought is it would not be clear.
Am I doing some calculation wrong, right? This is 2j omega term will come or not? Sorry, I think there is a minus term, right?
Yes, yeah, yes.
And then it becomes, as a tends to 0, this will be 0. So this is 2jb omega by omega square. So this is actually 2jb by omega. So this is the Fourier transformation actually of this particular signal. Right. Okay. So the last question for today. What is the Fourier transformation of ut, step function? Okay. So start like this. Ut is actually can be written as half plus half of signal function. I think this is known to everybody. And this is actually representation of signal. So for simplicity, I also drawing the what is signum function actually. So this actually takes a value of 1 for t greater than 0. And otherwise, it takes -1 for t less than 0. So if you see, this is the signum function actually. And you adds up 1, then what happens? This becomes like this. So this becomes 2 and this becomes 0. This whole term. And that's why to represent a unit step, we're just dividing it by half. So that is, if I get it, it is actually, next step is, if I take the whole one, then it is 1 t greater than t tends to 0. So this is actually unit step function. Now, in the previous case, we also derived this signal. The reverse signal, sorry. So this can be followed from the duality of that particular signal. But here I am just deriving from the signum point of view also. So basically we can write Fourier transformation of u of t is actually Fourier transformation. The signal x t e to the power minus j omega t dt. Now it is actually xt is out. For our case it is ut e to the power minus j omega t dt. So from here we can write it is actually minus infinite to infinite half of 1 plus signum function e to the power minus j omega t dt. So it is actually half minus infinite to infinite e to the power minus j omega t dt plus minus infinite to infinite signum function into e to the power minus j omega t dt. Now this is equals to this one, this whole one becomes half of Fourier transformation of 1 plus this whole term actually half of, sorry, there is no half term. This is actually Fourier transformation of signum function. So this is actually 2 by j omega. Like in the previous one, we just got it b is equal to 1, but it was a reverse function, so this actually 2 by j omega term comes from this equation. If you just take the, for our case, we have taken this type of signal. But if we take the signum function, which is this one, it will have, if we calculate in a similar way, we will get it is 2 by j omega. So this has 2 by j omega. And also this Fourier transform of 1 is actually half into, from the duality property, it is 2 pi del omega. Remember, we had calculated the Fourier transform of del function in the beginning, and we got it is 1. And from the duality property, it gets multiplied by 2 pi factor. So both of them comes from the duality factor that I have derived in the, throughout this whole assignment. So it is actually pi by del omega plus 1 by j omega. Sorry, so it's actually whole bracket. Here it is also actually the whole bracket. I missed it. So ut, that is actually half of 1 plus signum t as a representation of pi of del omega plus 1 by j omega from the linearity property of Fourier transforms.
Sir, why don't we take the U of t directly? Like, why
Which
use?
one? U of t directly, right?
Yeah.
But if you take U of t directly, then you have some problems. Like, I'll show you. So you have to take the integration infinite to infinite. U of t minus j omega t dt. But this signal does not converge at infinite. Actually, it actually becomes constant. Some integration problem will come at that instance, right? Because how do you express it? Actually, it becomes 0 to infinite. A to the power minus j omega t type of thing. And then at infinite, t tends to 0, t tends to infinite, you cannot easily do this integration because it's not actually converging.
Oh, okay. It's diverging. Oh, okay.
Yes.
Uh,
So you can do it actually. I have shown you from the duality property. It's not that it cannot be done from that property. Uh, Even I can calculate that also if you want actually. Do you want it?
yes, sir. Yes.
So basically it's nothing. Just like this. So it becomes what? 0 to infinite e to the power minus j omega t dt. It becomes e to the power minus I omega t by minus I omega. And this is 0 to infinite. So as t becomes infinite, this e to the power minus I omega t tends to 0 if omega not equals to 0. Only the condition that omega not equals to 0. And at t equals to 0, it becomes e to the power minus I omega into 0. That is equal to 1. So from this, we can say that this 0 to infinite e to the power minus I omega t dt is actually 1 by I omega. Because this I omega term will come. Okay, till it is clear.
Yes. Yeah.
Now the problem is this 1 by I omega is not particularly valid for omega equals to 0 because it will be infinite, right?
Yes. Yeah. Okay.
So that's why we just write it as 1 by I omega plus pi of del omega.
Okay, we need to represent at t
This,
equal to
the,
0, right?
at t,
Okay.
there is the problem. That's why we have to incorporate this term actually.
Okay, sir. Got it. Thanks.
Okay. So do you have any extra doubt for today's session?
Nothing as of now, sir. If there is any, I will ping you in the WhatsApp through document.
Okay, okay. You can ask next session, right?
Oh, okay. Okay, sir.
Okay.
Thank you, sir. Thank you, sir.
Thank you. Yeah.